And now we can extend our ideas of stoichiometry to solutions. So last chapter we talked about stoichiometry, but we could only talk about things like going from one mass to another mass. We weren't talking about solutions. Now that we're talking about aqueous reactions, which basically occur between two reactants that are each in solution form, we can talk about solution stoichiometry. So the steps are basically going to be the same when we do stoichiometry. We still need to have a balanced reaction. We still have to figure out what is the substance that I know the quantity of and what is the substance I'm trying to figure out. However, when we move to trying to calculate how many moles of the given we have, we're now going to use the molarity equation, rearranged to form moles is equal to the molarity times the volume. So when I'm starting with, I want to know how many moles I have, and I know I have 17 milliliters of 0.25 molar substance, I can calculate the number of moles from the molarity and the volume. So if I had how many grams of sodium chloride can be made from 30 milliliters of 0.150 molar CaCl2, I would first need to know what the reaction is. So I'd have to begin with this reaction. So calcium chloride reacts with silver nitrate to make calcium nitrate and 2 silver chlorides. So I want to know how many grams of silver chloride can be made from the calcium chloride. So first, I begin with calcium chloride would be my A and silver chloride would be my B. So I'd start with the calcium chloride. It says 30 milliliters of 0.150 molarity. I know that the molarity times the volume, but the volume has to be in liters, will get me my number of moles. So 0.150 moles times 0.0300 is going to get me 0.00450 moles of calcium chloride. Now I can go from moles of E to moles of B using the coefficient ratio. There we go. So it turns out since we're starting with calcium chloride, we'd put a 1 for the coefficient of calcium chloride on the bottom of the conversion factor. We put a 2 moles of silver chloride on the top, and it turns out that this will make 0.0900 moles of silver chloride. Now I go and I look back at the original problem and it wanted grams. I have moles of silver chloride, I need grams of silver chloride. Grams to moles is going to be using the molar mass. And so in this case, it's 143.4 grams per mole. So it turns out I can make 1.29 grams of silver chloride. So we're combining some solution information with the traditional stoichiometry we learned in chapter 7. You're now going to start seeing that you have to make decisions about which mole equation to use when you're doing stoichiometry. So we will, in the context of chemical reactions, and we're doing this, a lot of times it will be molarity times volume. So I will identify that if I have a substance in solution, I'm seeing at the end it's talking about aqueous, or it's telling me volume of that solution. If I have a substance that's in its pure or liquid state, and solid, it's pure state, but it's either like a solid or a liquid, and I could weigh the pure amount, I can use molar mass if I know what that substance is. So we did that all of chapter 7. We'll continue using it sometimes. And we haven't gotten to gases yet, but once we get to chapter 10 or chapter 9, I think chapter 9 is gases, if it's in the gas state, we'll have another equation that relates properties of gases to the number of moles of gases. It has to do with pressure and volume and a gas constant and temperature in Kelvin. So again, we're just taking the same steps that we did. We're still going to write a balanced equation. We're still going to determine what substance is given information about, and which is the unknown. Now, in solution stoichiometry, sometimes I have all the numbers I need for one substance of the reaction and only some of the numbers I need. So for instance, for solution stoichiometry, we need molarity and volume to determine the number of moles. If I just have the volume or I just have the molarity, that could be my unknown, the thing I'm trying to find. But one of them, I have to know both. I'd have to know the number, the volume and the molarity, and that would be my given. And then I'm going to calculate the moles of the given substance, same as we did before, but here we're probably going to be using the molarity formula. And then I'm going to use the coefficients to determine the moles of the unknown, and then I look at the problem to determine what units I need it in. Is it asking me for molarity of the the thing I'm trying to find? Is it asking me for grams of the thing I'm trying to find? Or is it happy with just moles? So this is another example. 10 milliliters of 0.3 molar sodium phosphate solution reacts with 20 milliliters of a 0.20 molar lead nitrite solution. And what mass of precipitate will form? So this is a limiting reactant problem. And we have it worked out. Again, I'd still do the same things I was doing. I'm going to identify my two givens. I'm given both the molarity and volume of both sodium phosphate and of lead-2 nitrate. So I would have to determine for each one of them how much of the precipitate I can make. In this case, the precipitate is the lead phosphate. So I would do it twice, and then I'm looking for the smaller answer. In this case, the 0.00133 moles of lead phosphate is smaller than the one I got from the sodium phosphate. So because 0.01133 is smaller than 0.0015, I can determine that this is the limiting reactant and this is the theoretical yield in moles. And then I could just convert that to grams for only the one that was smaller. I cannot compare the number of moles of sodium phosphate and lead phosphate, meaning lead nitrate, because those are different substances. But once I've used the coefficient ratio and I've gotten moles of the lead phosphate, now I can compare those moles, and whichever is smaller is the one I continue on with to get the actual grams by multiplying it by the molar mass. Here's another example. Again, tougher because now they're not really telling me the chemical formula. So I'd have to come up with the chemical reaction, figure out a lot of stuff, look at the information. In this particular case, this is not a limiting reactant. It's only one given because it's giving me the molarity and the volume of the silver nitrate, but it's asking me about sodium chloride. Again, I would follow through. Here I'm going to use the molarity and the volume to find moles of silver nitrate. Convert it. In this case, it's a 1-to-1 ratio, so it's the same number of moles of sodium chloride, but now I'm talking about sodium chloride, and then use the molar mass to determine the grams. A third example is one with HCl and NaOH, and this one is asking what volume do I need of the HCl solution. This is much trickier because even if I know the reaction is HCl plus NaOH makes water and NaCl, then if I'm looking at it, if I don't write them down, it may look like I have two givens, but I don't. I don't know everything about HCl. I know its molarity, but I don't know the volume. That's what it's asking. What volume of the HCl? So, but I do know everything I need to know about sodium hydroxide. I know the volume, I know the molarity. And so from that, I can find the moles of sodium hydroxide, use the coefficients, they happen to both be 1, to get the moles of hydrogen chloride or HCl acid, and then convert that to molarity because the moles divided by liters is molarity. Oh, actually, this is liters. So I have the number of moles, I know its molarity, I can use molarity as a conversion factor and convert it to volume of hydrochloric acid. So this would be in liters. I'd get that answer. If I wanted milliliters, I'd have to convert it over to milliliters. Another example, this is a very hard one that we used to have in our old textbook, and it's asking about mass percent. Again, it's not asking me for grams. It's not asking me for molarity. It's not asking me for volume. It's asking me for mass percent. But mass percent is related to grams. So in this particular case, and this is a lot of decoded weird stuff in here. Again, I would have to figure out what is the chemical reaction. I would have to figure out what information I'm given. In this case, the 0.3518 grams sample is the sample with the contaminant in it, but also a lot of water in it. And so that can be misleading. And so that's going to be held off till the end. So then I would solve for the problem and determine how much of this benzoic acid was in there from the titration with this sodium hydroxide. And from there, I could then come up with a mass percent is the mass of the part, that's be the mass of the benzoic acid out of the mass of the whole sample, which was the 0.3518. So you can see some really challenging problems in here. Let's go back through, though, again with the steps. Again, this is reminding you, these are the problems. Write the correct formulas of all the substances, make a balanced chemical equation, identify your given information and what is your given substance, what is your unknown substance. As we get into these solution and gas problems, they're not so obvious which one is which, because you may know some information about one of the chemicals, but not all of it, so it could still be the unknown thing that you're trying to find. Convert to moles. Again, how we convert to moles, now we have several options. In Chapter 7, all we had was either it's already in moles or we would be dividing by the molar mass. But now I might use molar mass if it's in grams and I have a solid or a liquid pure substance. I might be using molarity formula if I have a solution. I might be using gas pressure if I have a gas problem coming up in a few chapters. And then I'm going to use the coefficient ratio in step 4 to convert from moles of what I know to moles of what I'm trying to find out more information about. And then I have to go back and say what information, what does it want about that? Does it want moles? Does it want grams? Does it want molarity? Does it want volume of an aqueous solution? So from that, I'm going to have to alter. Step 5 is now going to be much more complicated. So 3 and 5, those steps become much more complicated because there's a variety of different ways I can do it depending on what is the given and what is it I'm trying to find. Again, we still could do limiting reactant problems just because you love them so much. And in that case, and I would recognize it if I were given complete information about 2 reactants. And they don't have to be complete in the same way. I might know the mass of one reactant and the molarity and volume of another reactant. I can still find how many grams how many moles I can make a product for each one of them, determine which is smaller and which is the limiting reactant, and from there continue on in the problem. Just visually, what we're trying to say is that all stoichiometry problems, I have to somehow get what I know 2 moles of A, and then go from moles of A to moles of B using the mole ratio. And then somehow from moles of B, I got to get to what I'm trying to find. And there's a variety of paths. So I can use density and volume to get to grams, and grams to get to moles using molar mass. I can use molarity and volume to get to moles of A. If I had atoms or molecules, we did that in Chapter 5. We could use that, or Chapter 4, we could use that to get to moles. Or if I knew gas properties, I could use the gas properties to get to moles of A. So I have a variety of different schemes to figure out how to get moles of what I know. And then I use the mole ratio to get to moles of what I don't know. And then from there, I can go from moles to molarity or volume, from moles to grams if it's a pure substance, from moles to atoms, or from moles to a property of a gas if it's in a gas format. So I now have a very complex web of options, and that's what the steps do. The steps really help you sort through where are you at and what are your options. Here's another example of a problem. And yet another example of a problem that we will do we can do those in class.